and don't even give us the filtering lengths. So multi-scale analysis, this has been largely developed at WPI, particularly the geometric multi-scale analysis. And we've had patent, and it's in the standards, and it's actually the stuff we've developed is being used literally all over the world. And so what this is we're looking for analyses that are supplied systematically over a significant range of scales. So we're going to look at scale specificity that we didn't look at before. And we need many more than the traditional 4 ranges of scales that we were just looking at. So these are much too coarse to qualify as true multi-scale analysis. We need characterization parameters that are computed across a range of scales. And then we need to do correlations and discriminations based on scale. So the characterizations and multi-scale characterization change with scale in a deliberate, detailed, systematic way. And then we're going to do scale-based discrimination or scale-based correlations. And I'll show you some examples in a moment. Now, historically or conventionally, there are a number of multi-scale things that you could use. One, you could adjust the filtering, the conventional filtering, to do multiple band passes. And I'll show you an example of that near the end of the talk. Autocorrelation function is Fourier's structure function and wavelets are all ways that we get from mathematics, and they're convenient because they're included in lots of software packages. So there's really no sweat. You just take your measured data and then put it into some mathematical package, and you can put this stuff out. The things that these are lacking are clear physical interpretations. So these are all largely developed at WPI. Slope scale we haven't done much with, although it's closely related with area scale. So these are done systematically over different scale ranges. So length, this sort of comes to us from Coastline of Britain problem. Maybe some of you are familiar with that. It's called Richardson compass or the coastline method. And that looks at the length of profiles. Area scale just takes that up another dimension and sort of plays on Vermont would be as big as Texas if you flattened it out, which turns out not to be true. Slope scale is similar. At a large scale, most of our surfaces have little slope to them, or none. But as we look at very fine scales, we notice that the local slopes are much steeper. Filling scale, how much stuff can you fit into the roughness on a surface? And then curvature scale, and we'll look at that in more detail in a moment. So to do a multi-scale analysis, some people think you need to take multiple measurements at different scales. You can, but all of the microscope systems that I've worked with change when you change the lens or even the electronic zoom. And so that the multi-scale analyses don't overlap always as we switch the scale. The RA may appear to, but that's because it's so non-critical. So for multi-scale, I discourage this. And there are multiple scales in a single measurement, starting at the sampling interval and going up to the size of the measurement. So that's why there's a circle around this one. This is the one that we prefer at this state in microscope development. Anyway, so from these multi-scale measurements, or exploiting the different scales of the measurements, we can do multi-scale characterizations. And then we can use the multi-scale characterization and multi-scale analysis of discrimination and correlation. And then we can look at, then we can see where we get the strongest correlations, the most confident discriminations, at what scale. And I'll show you some examples of this. So after doing length scale, which I started doing in Switzerland, and also began a crude area scale in Switzerland, I came to WPI in 1989 and found that we had lots of very good programmers as undergraduates, and we started working on area scale, and it's now in international and national standards. And so what it's based on is a tiling algorithm. We use triangular tiles, and we look at the surface with all the ups and downs, and then normalize it by the projected surface. So the projected area here is staying the same. This is a measurement with finer and finer tiles, and we can see that the number of tiles, of course, goes up as they get smaller, but it goes up by more than it would if it were a smooth surface. So the relative area tells me, in this case, I've got now 0.11% more area than I had well, almost, anyway. Relative area goes up, scale goes down. Now, this doesn't appear to be going up very dramatically, and that's not the key question. The key question is, can this help us discriminate or differentiate or discern two surfaces or two groups of surfaces, or can it help us with correlations? So here's another example. This is a very early one, and as a result, it's the one that we often put in the standards for area scale. Here's the tilings, and this is a diamond coating on a silicon substrate measured with a scanning tunneling microscope at UNC Charlotte, where I had some friends. So using large triangles, the relative area is fairly small, and here you can see we've got almost 50% more area than we did at these larger scales. The scale here is in the thousands of square nanometers, or fractions or whole numbers of square micrometers. So as we take a look at this surface and do a plot, let's take a look at a bigger image. We can see here's the scale, log scale of the scales, starting from 10 square micrometers going down to less than 1,000 square nanometers. And here are the relative areas. So very smooth surfaces should be approaching 1. And so that's what we're seeing. At the largest scales, the surface looks fairly smooth. And then we have this region where and this is a log-log plot, where this seems to be a constant slope. And so this is going up and showing us that it's got sort of repeating patterns of little pyramids over big pyramids. And we can kind of see that. So here's the scale of the little pyramids or little crystals on big crystals. And then at the lower slope, when we're tiling, or the finest scales, we have a lower slope. And this comes from the tiles now being smaller than the facets on the crystals. So here we can see some crystal facets, and now we're tiling on those, and those are relatively smooth. So from the point of view of irregularity or complexity, it is related to the slope of these curves. The greater the slope, the greater the complexity. And that's what we're seeing here, or greater irregularity, if you like.